we're both very excited to be here today. We've got a load of cool stuff to show you. As you can probably see, we've got a whole load of equipment up here. So we've got some live demos, we've got a musical performance, and we've got a whole lot of live coding. So anything might happen. Hopefully, you're going to leave here today excited about the opportunities on Android and Chrome. But before we start, a talk about Android and Chrome, it's a bit strange, right? Are we friends?
Well, I thought we were more family as Google, but anyhow, we have a lot more in common than you might think. For starters, both platforms have teams who are passionate about empowering users to be more musically creative. And we also have a very similar audio programming model, right?
Right. So both Android and Chrome have a callback-based audio programming model. You have an audio renderer, which is responsible for communicating to the underlying audio hardware. And every time it needs more data, it gives us a callback. There's a similar story with round-trip audio latency. And recent advances on both platforms mean that there's a very similar level of latency. On Android, all Pixel devices have around 20 milliseconds input to output latency. And we're now seeing devices from Samsung, Huawei, and others reach a similar level of performance.
The audio latency of Chrome browser largely depends on underlying operating system or hardware. But for example, the device round-trip latency of Chrome Pixelbook is around 20 milliseconds, which is good enough for most of our real-time use cases.
Again, with MIDI support, very similar capabilities on the platforms. In Android, we have the MIDI Manager API introduced in Marshmallow. And in Android Q, there's a new API called AMIDI, which is for high-performance processing of MIDI data. And
Chrome has had WebMIDI API since 2015, and it still remains the same.
Of course, one of the biggest features of both platforms is the number of active users. Android has over 2 billion users.
It's fantastic, and Chrome also has a similar number.
Now, obviously, some Android users are also Chrome users. So it's not like 2 plus 2 equals 4, but we estimate that by targeting both these platforms, you can reach around half the world's population, which is pretty incredible when you think about it.
And a company which has been taking advantage of this incredible reach is BandLab. They achieved huge growth thanks to their cross-platform approach from the beginning. Here's their story.
This is a story of how 3 people connected via a free music app collaborated to create a top 10 commercial dance track. The app is BandLab.
BandLab is a social music platform that enables our users to create and collaborate on music on all platforms, anywhere in the world, all with unlimited cloud storage. We have a Chrome-based digital audio workstation we call the Mix Editor. It allows our users to create and record music live, create their own tracks using our built-in instruments, or start a song from the thousands of free loops in our extensive library.
Here are our 3 creatives. Andy is an international producer with 2 decades of experience. He's based in San Francisco, but works around the world. Sehwan Kim is a pioneering guitarist, singer-songwriter, and arranger from South Korea. He works with leading K-pop and US artists, and is on Hollywood's Rock Walk of Fame. Lena London is an up-and-coming pop and R&B vocalist. Proudly repping East London to the world, she's a hopeless romantic with a golden voice. These 3 wanted to create music and needed tech that worked for them, no matter where they were.
BandLab, with the use of Google Chrome browser, we were able to remotely work with our CEO, Andy, in London.
Actually, the production was a big challenge in the beginning, since my team, the artists and the co-producers, were all in different places. And that's when I found BandLab on Chrome browser.
And we were able to do edits, saves, and share them in real time. So this was a really cool experience for us.
I'm sure this kind of web audio technology will definitely be a great gain for producers like me.
Thank you for bringing this technology to life.
I love seeing stories like these. What these guys are doing with BandLab is exactly what we had in mind when we were building it. Our vision is for a future where there are no boundaries to making and sharing music. This project shows how musicians can use BandLab to overcome barriers like distance or incompatible technology to connect and make incredible music. On mobile, we've been working hard to create music editing and creation tools to empower everyone with access to a phone. And as the most popular operating system in the world, Android is a major engine to drive that. Today, we have close to 7 million registered users, and they're saving almost 2 million new songs every month on BandLab. A huge portion of our community is collaborating via Android and Chrome. We are here to democratize music, and that's now possible thanks to developments in technology and partners like Google.
So BandLab has been successful by targeting both Android and Chrome. And today, we're going to show you how you can do the exact same thing. To do this, we're going to build a synthesizer app, which runs on Android and runs on Chrome, but shares the same code.
That's right. We'll be using the exact same synthesizer code written in C++. And Donnie's going to show you how to make it work on Android, and I'll do the same on Chrome.
After that, we'll add MIDI support to both apps. Hongchan will do that for Chrome, and I will do it for Android. So I'm going to start, and I'm going to start by using a library called Oboe. Now, Oboe is a C++ library for building low-latency, high-performance audio apps on Android. Here's how it fits into an app architecture. So we use the Oboe library to build an audio stream. That's responsible for communicating to the underlying audio hardware. In this case, I'll be communicating with this Pixel XL headphone output. Each time the audio stream requires more data, I get a callback into my app. And my job is to add in a synthesizer, which will then be responsible for rendering audio frames back into my audio stream. OK, if we could switch to my laptop, which needs Hongchan's password. OK, so I'm in Android Studio here. Hopefully, you can read the code. So I've already built kind of a Hello World audio app, and it has this one class, Audio Engine. In Audio Engine, we have a couple of methods, which the most important ones are start, which is called when the application starts, and this onAudioReady method, which is called every time my audio stream needs more data. So that's going to be being called every few milliseconds. And I'll cover the rest a bit later on. But so Hongchan and I are going to be sharing source code, and here's the source here. So what my first stage is I'm going to include the synthesizer header. I'm now going to create a synthesizer object, and we'll just make that a unique pointer of type synthesizer. OK, now I'm going to go into the implementation of this class. So in my start method, I'm going to create an audio stream, and this class is provided by Oboe. It allows me to build an audio stream, so I set a few properties on my stream. For example, low latency to get a low latency audio stream, and I also set the format to floating point samples because that's the format of my synthesizer. I then open the stream, and I can now create my synthesizer object. So I'll just do make unique. OK, so in the constructor for my synthesizer, I have to specify the sample rate. And that's the rate at which I'm going to be generating frames of audio data. And I get that from my stream. Now, the reason I have to do this at runtime is because the sample rate of my audio stream will depend on the underlying audio hardware. OK, so that's my synthesizer created. Here's my audio callback, the one that's being called every few milliseconds. At the moment, I'm just outputting silence. So I'm going to get rid of that and have my synthesizer render its data into the audio stream. And the way that I do that is I have to pass data into this container array here called audio data. Now, you notice that it's of type void star, so I need to cast it to type float. So I'll just do that now. And my synthesizer also needs to know how much data to render, which is this num frames parameter here. Right, so almost there. My synthesizer is now able to render information into my audio stream, but I need to add a bit of control. So I've added a couple of methods here. The first one is onTouch, which is going to be called each time I push my finger down onto the screen and each time I lift it off the screen. So this parameter here is down will be true if I'm touching down and false if I'm lifting off. So I'll just say if the touch event is a down, then tell my synthesizer to switch a note on, and I'll just specify kind of a random note here, note 60, which is middle C. Otherwise, if I'm lifting off, then I'm going to switch the note off. So the last thing I'm going to do is add a bit more control to my synthesizer, and I thought it would be nice if I tied the rotation of this device with the filter cutoff of my synthesizer. So I've got this method here, onSensorExChange, which is going to be called each time the value of rotation changes. This comes it'll be a range of values between -1 and 1, so I have a kind of some scaling and some mapping here to get it into the value range expected by my synth. So here we go. Ignore the red, that's just Android Studio. Okay, so I'm going to run this app, and what should happen is when I tap down on the screen, we hear a sound. And when I rotate the device, that sound should change. So moment of truth. Okay, so the first part done.
OK, it's my turn now.
Yeah.
So before we move on to the code editor, I'd like to talk a little bit about how this whole thing works on web browser. So let me go back to the slide. So obviously, we cannot use the same C++ source code as is, so we need to go through a few steps to make it work. So first, we start from the source code synthesize.h. This class has methods like not on and not off a render, and that needs to be compiled with mscripten, the LLVM-based compiler that compiles C++ source code into WebAssembly, or WASM for short. So ultimately, we will end up with the synthesizer WASM.js file, and the JavaScript object from this WASM module will have the same method that we exposed, which is not on, not off, and render. But this mapping just doesn't happen automatically, and that's what mscripten binding API is for. So I'll be creating a new C++ file for this binding work. And this file will include the original source code and will be compiled by mscripten. This whole process will give us the WASM synth code, but how do we make sound from it? That's where AudioWorklet comes in. With AudioWorklet, you can use Web Audio API's rendering thread to run JavaScript code and make sound from it. It exposes low-level audio callback, so we can hook up our synthesizer's render function in there. You can search AudioWorklet for more information. So there are several moving parts in AudioWorklet system, so let me illustrate how it works. First, we're going to use AudioWorklet processes to wrap this WASM synth module. This is because this class has the audio callback, and this callback gets fired about every 3 milliseconds, depending on your sample rate. And the process side, the whole thing, is handled by the audio thread, and the scope is isolated, so it's very good for audio processing. And all of this stuff goes into a separate file, synthprocess.js. But at this point, we cannot control the processor because it's in the other thread, the audio thread. That's why we have something called the AudioWorklet node. It's a main thread counterpart of the processor. So, but then how do they talk to each other? And for that, we have something called message port. So this message port allows these two objects talk to each other asynchronously. For all the main thread business like UI and MIDI, that goes into index.js file, and that's our main script file for our demo application. OK, I'm going to switch back to my code editor. So let's talk about this file first. This file is our binding file. So first, I need to include this synthesizer H source file here. That's happening right here. Then actually, I'm extending the original synthesizer class to create a small, thin repo class. But why do I need this? That's because Emscripten's binding API is a little bit picky about having raw pointer to the floating point array. So actually, what I'm doing right here is I'm doing manual typecasting to work around this issue. It's a little bit odd, but please bear with me. You can look up Emscripten's binding API's documentation for more detail. But what I'm doing right here is after the manual typecasting, I'm calling the original synthesizer's render function. So let's take a look at the second half, the bottom half of the file. This is where actual binding happens. So for the first 4 lines of code, basically what I'm doing here is I'm exposing the function of the original synthesizer class. So I'm exposing constructor and not on function and not off function, right? All of those functions is already used in Don's demo. Then I'm exposing the render function from the repo class, which this function is with a little workaround that we wrote above. So that's our binding file. So I think we're ready for the compilation. And for the compilation, I already set up the Emscripten compiler on my machine. So we can just do the compilation. Let me check out our directory first. So I'm going to move on to our WASM file directory. So for the easier compilation, I already set up my make file there. So I'll just type make here. And compilation is completed. So if I click this link over here, actually we can take a look what's happening inside of this WASM file. In the beginning of file, it just looks like a random JavaScript file. But if I scroll down through enough, kind of interesting things are happening over here. They just look like assembly code. So anyway, this is our WASM Synth module. So let's just move on. And then this is our synth process.js file. And this is where all the audio-related operation is happening. So first step I need to do is I need to import WASM Synth module that we just compiled. So now we have the dependency set up. Then I will touch the constructor of AudioWorklet processor. This is the class that has audio callback. So we need to set up an instance of WASM Synth. So let me do that. Here, we have 2 lines of code. The first line is constructor, which is from C++ world. And so this is literally constructor that Don used in his demo. So I need to provide the argument for this constructor, which is sample rate. And this sample rate is a global property of this AudioWorklet global scope. It's not just random magic variable. And in the next line, I'm using a little helper called WASM audio buffer, and for easier WASM memory management. I'll get to that a little bit later. And this function right here is a process function. This is our audio callback in AudioWorklet system. So here, I need to call my render function there, right? This render function is also from the C++ world. So first argument of this function is actually raw pointer to the floating point array. So, but there's no way to get that raw pointer here. So what I'm doing, that's why I'm using my little helper for WASM memory management, because this utility function will give me the address of WASM allocated memory block. Then I'm doing one more step because the memory space provided by WebAudio API and WASM allocated memory, and they are completely separated. So I need to actually copy the data rendered by synthesizer to the WebAudio API's output buffer. So it's just one more step to clone the data. For that, I'm using typed arrays set method, and this method uses memcopy internally, so it is supposed to be super fast. So that's done. Then let me write one more function, because I like to have the similar functionality with the Don's demo. Don uses onTouch function to create a test tone, right? So here I'm creating play test tone function. It's pretty much the same thing with what Don did in his demo. So when is down, is come, basically I can trigger not on, and when button is up, I can trigger not off. I'll be using the same 60 middle C, right? So now we have this handling function setups, the very last step here is I need to set up my message port. So if any message from the main thread, it comes from the main thread, I can trigger my play test on function. So I think we are almost ready with the sinceProcess.js. This is the very last step. What I'm doing here right now is I'm registering the sinceProcessor, the custom class definition, under the name of my synth. So this will be keyword for my class. So let's remember that. So I'm going to move on to my index.js. This is the main script file. So first step, what I'm doing here is I'm creating audio context, which is a gateway object for WebAudio API. So that's what I have. Then I'm going to set up the minimum audio graph to test this demo. So here I'm using AudioWorklet add module. This is how to load custom process definition into WebAudio API side. So I'm going to type the file name of sinceProcessor. And once the module loading is completed, I can create AudioWorklet node based on the keyword that I used for the registration. And then I'm using a small gain node because I found that my synthesizer was too loud for the demo. So I'm a little bit of lowering my volume there. Then I'm creating audio graph from synthesizer to my volume controller and the output of this laptop. So that's kind of really minimum audio graph. And let's look at the next function right here. This is on button change. And I already set up this button with the page on my this test page button over here. So right now, if I do anything like this, nothing happens because this on button change has nothing there. So what I want to do here is I have to send this isDown variable to message port, and so it can be delivered in the AudioWorklet processor side. It's really simple. That's pretty much what I will do here. So I think we are ready for the test tone. So I'm going to refresh the browser, and we'll activate the page in Audio Engine. That's our test tone. And let's move on to the next step. So I'll switch back to slide. So we just set up an AudioWorklet node and AudioWorklet processor and play the test tone. So next step is Web MIDI integration. And Web MIDI API provides us with different types of objects, but what we'll be using today is actually MIDI input. MIDI input literally receives a message from a MIDI device. And when that happens, it will fire on MIDI message event handler. So our job here today is basically sending any incoming message from this on MIDI message event handler and just pass them back through AudioWorklet processor. And all of Web MIDI integration happens on the index.js, but we still need to go back for AudioWorklet process just a little bit because our synthesizer processor is still not ready for incoming MIDI messages. OK, I'm going to switch back to my code editor again. So this is our index.js file again, and here's a place for the Web MIDI API. So I'm going to creating MIDI access object. That's the gateway for the Web MIDI API. And once I have that object, basically what I'm doing here in 3 lines of code is I'm iterating all the detected MIDI input in the system, and I'm assigning the same event handling function to all of MIDI input on MIDI message event handler. And the content of the event handling function is really simple as well. We're not doing any pre-processing here. We will just take the data, just send to the AudioWorklet processor. So that's done. I think index.js file is pretty much done. So I'm going to go back to sinceProcess.js because we need to fill this function in because handle MIDI event is currently doing nothing. So what I'm going to do here is basically these few lines of code because we only interested in node on and node off, 2 types of MIDI event. When MIDI event node on comes in, basically I'm going to trigger node on function in the synthesizer, just like this. And my argument will be node number, which is the second byte of incoming MIDI messages. And similarly, with the node off case, I can trigger node off method. All right. Okay, one last step. Currently, our own message event handler is tied to play test tone function, but this is not what we want, so we're going to replace with handle MIDI event. So if there's any incoming MIDI message to the processor side, our handle MIDI event function will get called. All right, that's done, I think. So I'm going to move on to my test page, activate the web page. With some luck, I should be able to play my synthesizer with little MIDI keyboard over here. All right, that's the end of my demo. I'm going to switch back to my slide, please. So we started, let me remind you one more time that we started from the same source code, right? And it comes with amazing benefits like less code to maintain, and also identical sound across two platforms, and so on. So you ready for the MIDI?
Sure.
Right.
OK, so Hongchan created a synthesizer app and added MIDI support to it. I've already created my synthesizer app. I just need to add MIDI support. And to do that, I'm going to use the new native MIDI API in Android Q. So this is a high-performance API that's designed to use inside your audio callback. But there's still a bit of setup work that you need to do inside Java. So I'll just talk through that. In Java, you need to listen for MIDI device connections. So when you actually plug in your MIDI controller, you will receive a callback, which allows you to open this device. You then get a Java MIDI device object, which you pass through JNI to the native API. You convert that from a Java object to a native object, and then you open an output port, so an output port on the device itself, which you can receive MIDI messages from. And then you can start receiving MIDI messages. Now, because we're short on time, I'm just going to focus on this very last part here, the receive MIDI messages. But there's source code online which shows you how to do the rest of this. So if we could switch back to the machine, please. OK, so I'm back in my audio engine class. And here's my audio callback. So this is the one that's being called every few milliseconds. And I've got this process MIDI method here, which is actually implemented down here. And this is going to be called, sorry, I'll just scroll back up here. This is going to be called before I render my synthesizer frames. So what I need to do is call a MIDI output port receive. So this is the main method that you use for receiving MIDI data. I've already set up an output port somewhere. So everything is in red because Android Studio's indexer has currently broken, which is going to make this incredibly fun. So the second parameter to this method is an opcode, and that can be either a data type or it can be a flush message. So if the opcode is set to data, it means there's new MIDI data available. If it's flush, it means that any MIDI data that you received before, you need to get rid of it because it's now stale. I also specify a buffer to actually store the MIDI message in. I tell the method how large that buffer is so that I don't overflow it. And I also specify a message size, which tells me how big that message was. Typically, this would be 3 bytes for a note on or note off message. And the last parameter is a timestamp. And that allows me to reorder MIDI messages based on the order that they were actually tapped by the musician. OK, so this gives me everything I need to receive MIDI data. So I just need to check my opcode to see whether it was data. And I'll also check the message size just to check that it's greater than 0. So we now know we definitely have a MIDI message. And as Hongchan did in his app, I just need to read the first 2 bytes of my MIDI message to understand exactly what the message was. So message. And I'm actually only interested in the first 4 bits of this MIDI message. So I just use a mask here, and we'll just have a quick look at that, just to get the MIDI status. The second thing that I'm interested in is the note, and that just comes straight from the second byte. So I can now say if the status was a MIDI note on, then I'm going to switch my synthesizer on. And I pass in the note. Otherwise, if the status was a note off, then I'd just send in a note off with the same note. OK, I think that should work. So I'm going to rerun this now. So this is deploying over this USB cable here. When I plug in this MIDI controller, I won't know if anything's gone wrong because I won't be able to receive logcat information. So what should happen is when I plug this in and I tap on a key, we should hear a sound. And I had a stuck note there, so there we go. So that's MIDI working on the Android app.
OK. So can we switch back the slide, please? So I think we're ready for the jam now. So I prepared a little backing track for us. So
yeah, we've got a backing track. We're just going to do a very short jam, see what it sounds like. Basically, because we've got a big sound system, so why not?
yeah. And Don will be playing the bass line.
Yep.
Right? And I'll be playing the lead synth with arpeggio activated. So let me change my setting real quick. All right, I think you're ready for the jam. So you ready?
OK, yep.
Can we switch back to the slide, please?
So I'm not sure that's going to be a #1 hit. But it was OK. It was OK.
Yeah, okay.
I think we can definitely benefit from some expert advice.
Sure. I mean, we can always improve, right? So how about asking someone who has been working on software synthesizer for more than a decade? Let's have Magnus Berger from Popular Head Software on stage.
Thank you. OK, so my name is Magnus Berger. I'm the CTO of Propellerhead Software in Stockholm, Sweden. Now, we've been around for about 25 years, or exactly 25 years, making music-making applications. Our most well-known software is called Reason. It's a virtual studio for Windows and Mac OS, and you can create any kind of music imaginable in it. So can we please have my computer? So this is what Reason looks like. It's essentially a virtual rack. That's the most well-known feature, into which you can drag and drop like synthesizers, effects. And the interaction model is such that you can push buttons, you can turn the knobs. Let's change the filter frequency here. You can see it change. And let's load a preset. And that must be the shortest Reason demo ever. So about 10 years ago, we wanted to open up Reason for third-party developers to create plugins. So we wanted to create a plugin format that's future-proof, and we call that rack extensions. We did that by making it sandboxed. But we didn't know exactly what kind of hardware architecture we were going to run on in the future. So you see, DSP code is usually written in C++. In our SDK, we hand out an LLVM-based toolchain. But instead of developers giving us the final binary output, they're handing us LLVM intermediate representation, the LLVM bitcode. It's sort of a semi-compiled platform-agnostic code, and then they upload that to our servers. And we run this App Store model with more than 500 plugins, and we do the final compilation towards the target architecture of the customer. And then we have a user interface. It's a declarative retain mode user interface, not unlike a web page, but this is written in Lua. So along comes all of this cool web technology with audio worklets and web audio, web MIDI. And the technology fit there is pretty much one-to-one with our philosophy of rack extensions. So we just had to make this internal tech demo. So this is not really a product. It's an internal tech demo. We had a lot of fun creating it. So we took this Lua code, the user interface definitions. We made it transpilers. We transpiled that code into JavaScript and HTML. We're taking the LLVM bitcode and building that into WebAssembly. And this is what you get. Opening up Chrome instead. So this looks sort of familiar, doesn't it? Vanilla Chrome, let's drag and drop Europa. Europa, it's a rack extension, so we can port that here. And sweeping the filter frequency. Let's open a preset that you've heard before. Now, this wouldn't be half as cool if it wasn't that we can take pretty much anything from our app store and just move it to the web using this build tool chain. So let's try something else here. This is Poly6 from Korg from Japan, a very nice synthesizer. And let's stack a player that's a MIDI effect on top of it. It's also a rack extension, so it's fairly easy to move that to the web. And changing the cutoff frequency. And the resonance. Pretty cool stuff, huh? So can we go to the presentation? So what could be better than helping people express themselves? Well, just maybe possibly helping even more people express themselves. And being backed by a platform that literally supports billions of users, that's definitely an enabler. And by the way, this also runs natively on phones. Back to Hongchan.
That was really impressive. Thank you so much, Magnus.
Thanks, buddy.
And having partners like Propeller Hats makes me really, really inspiring. And I hope this can be a positive signal to other audio developers as well. We have some stories to share, right?
Yeah, so I'm lucky enough to work with the leading names in the pro audio industry. And over the past 12 months, we've had some fantastic success stories. And I just wanted to share very quickly 2 of them with you now. The first one is from Isotope, a long-time big player in the world of audio processing plugins. They recently launched a product called Spire Studio, which is basically a mobile recording studio. And it comes with a companion app, which allows you to do multi-track recording. When they launched on Android, they saw a nearly 40% increase in sales. And this is absolutely fantastic because it shows that Android users have a demand for high-end audio hardware. Another success story comes from Music World Media. Just a few years ago, they were a tiny startup in Paris, and since then, they've launched an incredible number of successful apps and games in the musically creative space. And over the past 12 months, they've been able to acquire an astonishing 45 million new Android users all across the globe. And for me, this shows the incredible reach that Android has throughout the entire world. So some great stories there. You've got some stories from the website.
Sure. So things have been pretty great on the web world. So the web music ecosystem has gotten a lot more diverse, and these are my 3 favorite digital audio workstations on web. An audio tool is a fully fledged music studio with open-ended workflow. Its user interface is amazing. You can collaborate in real time. An M2 Studio, which I use for my backing track right there, it comes with high-quality sample libraries and instrument. And Soundation was featured in Chrome Developer Summit last year, and they have been pioneering cutting-edge features for WebAssembly. So it's amazing all of these tools are freely available today on the web. And then lastly, the Ableton. With their Learning Music web app, you can instantly start learning how to create a song by going through masterfully crafted content by step. And you can even export your work to Ableton Live from here. Ableton saw the potential of the web platform as an educational medium, and this project right here is a realization of such a vision. OK, let's wrap up what we talked about today. We showed you that both Chrome and Android are more than capable of doing real-time audio with MIDI support. And through the live coding demo, we showed you that you can use the same source code on both platforms. And finally, the enormous reach of Android and Chrome.
Yeah, so I just wanted to make one final point, which is I think it's very important to remember that music is a universal language. And it's something that's understood by everyone, regardless of where you are in the world, your cultural background, or economic status. And it can be a powerful force for good, for people to communicate. And with your programming skills and Android and Chrome's incredible reach, then we can give everyone the tools that they need to be musically creative, so that they can not just listen to this universal language, but they can speak it as well. Search for AudioWorklet and Oboe library to get started. Thank you all very much.